Okay. So hello everyone. So it's my great pleasure to introduce today's speaker, Bence Kocsis. So Bence got his PhD from in Budapest, then moved on for a postdoc in the US as in part as an Einstein Fellow. So I think he went IAS, then Harvard, then IAS back. Then got a position as an assistant professor in Budapest, and more recently, a few months before the start of the COVID time, moved to Oxford as an associate professor in theoretical astrophysics. On the side, he has also been the principal investigator of a NERC proposal called GalNuc, which was focused on statistical mechanics for galactic nuclei. So his interests are scientific interests are on the theoretical astrophysics side, in particular, gravitational wave astrophysics. I would say he's an expert of the dynamics of dense stellar clusters, and more generically, statistical mechanics for self-gravitating systems, and also black hole physics. As a side note, once again, to emphasize my pleasure of introducing Bence, I would like to mention that he has been an author of 2 papers, which I personally and clearly consider to be in my personal pantheon. So in one of them, in 2015, he devised the generic Hamiltonian framework to describe the jittering of orbital rotations in galactic nuclei, a process that is called vector resonant relaxation. And then more recently, with his PhD student Akos, he used this formalism to predict the spontaneous alignment of intermediate mass black holes around supermassive black holes. Doing so, he had to use a smart trick so as not to suffer from the quadratic difficulty of direct n-body approaches. And they emphasize together that galactic nuclei are highly non-trivial systems. They undergo non-trivial phase transitions, and in a sense, they are just like liquid crystals. So Bence is going to walk us through on the importance of active galactic nuclei as being key sources for gravitational waves, in particular as observed by LIGO and VIRGO. So it's my pleasure, Bence.
Thank you very much, and thank you for the kind invitation and for the great honor to talk to you. So indeed, I've worked a lot on dynamics in the past, but this talk will be more generally focused on gravitational wave sources. The big question now is to explain the detections that LIGO and VIRGO have seen. And one of the ideas, as I will discuss in this talk, is that galactic nuclei may be factories of gravitational wave sources for LIGO and VIRGO observations. So some of the work that I will be discussing is in collaboration with my postdocs and PhD students listed here. And let's get right to it. So this is an extremely exciting time, because finally, since 2015, gravitational waves are routinely detected by LIGO and VIRGO. It's a completely new window on the universe that has the potential to bring information directly on space-time, which may be from regions which may be completely invisible in electromagnetic bands. So there's a great potential for big discoveries to happen. And so the Nobel Prize has been awarded for the gravitational wave discoveries already, but the interpretation of the gravitational wave sources is completely open. So the big question is how the black holes actually come together and how they merge, what types of environments are most common to produce the gravitational wave sources that are being detected. So I would like to encourage all of the young people in the audience that to work on this topic, because there's a big opportunity here to just come up with something completely new, which may explain the sources which people may not have thought about previously. So in this talk, I will be first discussing the status of the discoveries, and then move on to discuss some of the astrophysical models and some of the problems that they are facing, and then show you some new ideas to explain the sources. So this talk will focus on the high frequency gravitational waves currently accessible with the present instruments, LIGO, VIRGO, and now COGRA in Japan. But in the future, there will be other frequency bands that will become available, but I will not discuss this. So this talk will be concentrated to the high frequencies, which are mostly believed to be, the frequency regime where you can detect stellar mass black holes and stellar mass compact objects like neutron stars. And of course, there may be other things which we don't know yet. So that will be very interesting to see. But what LIGO has already and VIRGO already detected were mergers of black holes and neutron stars. So here I'm showing some of the waveforms that have been detected, which were then interpreted as being mergers of black holes and neutron stars. So you generally see these oscillations of space-time, frequency is increasing and the amplitude is increasing, and then it decays. And there's after the merger, there's practically no signal. So there's now a big zoo of detections. So here I'm showing the masses of the different mergers, and you can see that LIGO and VIRGO has detected these blue dots, which are believed to be black holes. And here, for example, you see on the left, you see a black hole, let's say 18 solar masses merging with another one at, let's say, 25 solar masses and producing something which is a bit less than the sum of the mass of the black holes, because gravitational waves take away some of the mass. And so they form a merger remnant. So you can see this whole process from the beginning to the end, from the last few seconds of this process, or sometimes even less than a second, where these two black holes combine to form a merger remnant. There are other points in this figure that, in purple, which are individual points. So these are individual compact objects, not in, for example, black hole binaries, but orbiting around the star. So you can have a star orbiting around the compact object, a black hole, a neutron star, and the star can deliver mass onto the black hole. And during this process, there's a bright emission in X-rays, which can be used to detect the mass of the compact object. So this method has been used to detect black holes before LIGO and VIRGO. And the masses shown were found to be between, let's say, 8 solar masses and, let's say, 15 or 16 solar masses. So it was a bit surprising that the LIGO discoveries have shown much higher mass stellar mass black holes in the universe. And you can see that there are some interesting events here where a low mass black hole was merging with a high mass black hole, or a neutron star was merging with a black hole, for example, and producing another black hole. And there were mergers of neutron stars, and of course observations of neutron stars in the past. And now you could detect the gravitational waves from the mergers of neutron stars. So this is all very exciting. And just by using gravitational wave observations, you can detect the parameters of the sources. So here's a list of the detections and some of the confidence regions for the different parameters that can be detected that have been detected with LIGO and VIRGO. So you can see, for example, the mass of the first component and the mass of the second component. And there's the mass ratio, which has obviously a large error bar. And there's the effective spin parameter, the chi effective, which is the component of the spins projected onto the angular momentum vector of the binary. And this can be measured, and also the distance of the source. So, so I will not discuss many of the features of these detections, but here's one example. You can measure the mass distribution of the black holes, of the merging black holes, I should say. And here I'm showing this is from the LIGO paper that shows the distribution of the primary black hole mass. You can see different curves corresponding to different models. So depending on what you assume in the model, you can optimize its parameters to best fit the data. So you get then different curves. But as you can see, the general feature of all of these curves is that it generally extends to high masses. So this is something that should be noted. And this is already surprising because previously it has been believed that you cannot form black holes higher than 50 solar masses from stellar collapse because if the progenitor star is too massive, then it will start to oscillate and do pulsations, and the pair instability just carries away all of the mass, and you will not form a black hole with such high masses. So LIGO and VIRGO detections have clearly demonstrated that there are black hole masses in the so-called mass gap regions where you would not expect to see black holes. And the mass distribution seems to be top heavy. So a lot of mergers happen at high masses. But of course, this is because the most massive objects are easier to detect. They are detectable to larger distances. So if you take that into account, then the actual merger rate as a function of mass in the universe is not as top heavy, but still it's top heavy. So the slope is something like -2 or even less, -1.6. And the other thing that you can detect is the spin, as I was saying, the component along the angular momentum of the binary. And here are some of the detections of this component. You can see that it's generally clustered around 0, which is somewhat surprising, as I will show. And so then you can look for correlations between these parameters, for example, correlations between mass and spins. But you can plot individual sources on this diagram of this spin parameter versus the mass, but you don't see, there's no clear, obvious correlation here. So you can just see these large regions are the error regions. There are, of course, large errors in interpreting the data. There are different parameters could be consistent with the detections for individual sources. But you can see that generally chi effective is distributed around 0 with some outliers, which is highly non-zero, probably highly non-zero. But it's not, there's no specific trend with mass. The other thing that you can detect is the rate of mergers. And just using the first two observations, the rate has been determined to be between 2 and 600 per gigaparsec cube per year. And as newer and newer detections came along, the error bars have shrunk to 15 to 39 per gigaparsec cube per year at the moment. And for the neutron star coalescences, you have 2 detections at the moment, and the rates are between 80 and 810. And so then you can hope to detect the mass, so the redshift distribution of the rates, and this could be something that could be used to constrain the astrophysical models of these mergers. So there are many questions that we can finally address. One is, how did these black holes form and how did they evolve? So why do we see so many high mass black holes merging in the universe? How do the black holes get so close that they actually merge? This is already an interesting question because stellar binaries are usually at separations which are too large for gravitational waves to bring them close to merger within a Hubble time, within the lifetime of the universe. So you need to have an additional process which brings the black holes close. And it's an interesting astrophysical question, what this process is, how the black holes get so close that they can actually merge in less than a Hubble time. And then you can tune these models and examine these models and see if the mass, the spin, and the rate distributions match the observations, match the expectations. So as I alluded to earlier, electromagnetic observations have been used in the past to measure the masses of compact objects. And here I'm showing a different representation of this. So you can see that the detections are clustered around 1.4 solar masses. These are believed to be neutron stars. And you have detections around 10 solar masses, which are believed to be black holes. So this was previously. And so the question is, What about the objects that LIGO detects? Is this a different population, for example? So in this talk, I'd like to discuss the astrophysical origin of mergers, and let me just highlight some of the ideas that have been put forth to explain these mergers. So one is the standard isolated binary evolution. So obviously, there are many stars in the universe. 10 to the 11 stars reside in the Milky Way. And you can calculate if the stars reach beyond, if the stars have mass beyond, let's say 25 solar masses, they will turn into black holes. And so you expect to have 10 to the 7 to 10 to the 8 star mass black holes in a single galaxy. It turns out that massive stars reside in binaries. So the progenitors of the black holes are typically already in binaries. So then the simple idea is that maybe these binaries are the progenitors of the black hole mergers that LIGO sees. But the problem is that the separation must be very small for them to merge. So in that case, you have episodes of mass transfer between the stars, and there could be a common envelope, and ultimately you can form two black holes, perhaps at small separations, and merge them. Maybe a third companion in the vicinity of the binary can help this merger process. In fact, 25% of the massive stars are observed to be in triples, and the third object can gravitationally drive the inner binary to a merger. So this is one idea. The other idea is the dynamical environments. So some of the stars, so it's less than 1% of the stars in the universe are observed to be in very dense stellar systems, in systems where the density is up to 1,000 to 10 to the 5 times higher than in the galaxy. So these are globular clusters, which have sizes of between 1 and 10 parsecs, and also galactic nuclei. So at the centers of galaxies around supermassive black holes, the density of stars is even higher. So here the density can reach up to 10 to the 10 times the density in the Milky Way. And so in this case, you have a high chance for encounters. So two objects can just by chance come close to each other. And so this is a scattering process for which the encounter rate scales with the square of the density. And obviously the square of the density is much, much higher in these systems than in the galaxy. And so in these systems, you have a chance for dynamical encounters to form binaries, and then for dynamical encounters to have binary single interactions, for example, which can bring in the binary components to the small separations needed for merger. And there's another idea that maybe the dark matter explains the detections. So this is very tantalizing. If dark matter consists of black holes, at least in some part, then you can explain the LIGO VIRGO mergers. So obviously, most of the mass in the universe is in dark matter. So it's an interesting question. If dark matter consists of black hole, so dark matter particles are basically black holes, then what happens? So there was a paper in 2016 which claimed that if 100% of the black holes is made up of 30 solar mass black holes, then the merger rate that you predict by encounters between these black holes will be the same that LIGO has just detected. But so this was very exciting, but then there was a paper which showed that if that is the case, if you have so many black holes in galaxies, then they would disrupt globular clusters already, especially in dwarf galaxies. And there's an observation of a globular cluster that resides in a dwarf galaxy, close to the center of a dwarf galaxy, which could not exist if dark matter was made of these black holes. So the same authors went back, and in fact, they realized that they made a mistake in the original calculation. And once they fixed that, they find that you don't need 100% of the dark matter to be in black holes. Only even if 1% of them are in black holes, then you can match the rates. So, so that is consistent with this globular cluster and consistent with the LIGO observations. And in fact, if these primordial black holes form binaries already in the early universe, then you need even less than 0.1% of the dark matter. If it's in primordial black hole binaries, then you can already explain the high rates that LIGO sees. So this is very exciting, but of course the question is, why do you see, for example, the particular mass distribution that LIGO detects if it's all primordial black holes? And there's no strong reason to expect these types of masses to emerge from first principles. So it remains to be an exotic idea, but it's exciting. So I would like to discuss some of the problems with all of these ideas. So here I'm just showing some of the problems, and I will just go into more details in the following slides. So the galactic field binaries may have a problem with explaining the spin distribution, the mass distribution. There are theoretical questions about how to solve this so-called final AU problem, how to bring the objects within an astronomical unit for them to merge. How does common envelope evolution actually work? And for the case of triples, the triple companion can help to merge the binary, but perhaps not enough of them are expected to be in the right configurations for them to merge. For the globular clusters, only 0.5% of the mass in the universe is in globular clusters, and that may not be enough to explain all the mergers. Similarly, for galactic nuclei, also, although in that case, you can have multiple mergers per black hole. If every black hole merges multiple times in a galactic nucleus, then maybe you can explain the rates. And dark matter halos is just exotic. That's my only criticism. So at the moment, I would say that there's no single convincing theory to explain all of the observations. So option one, stellar evolution, has a lot of question marks. So here's one cartoon of how the evolution could take place. You have two stars. One of the stars grows into a red giant, forms a black hole, which may or may not be ejected during the formation from the binary. If it's not ejected, then you can have the other star to form a red giant, which if it happens to lie close to the black hole, it may engulf the black hole and maybe help the black hole to come in. But you can also eject the envelope of the star. So in the end, you can form a black hole binary, which may or may not be, so the other black hole may be ejected. But if not, then you can have two black holes at small separations, which then merge. And as you can see, only the last part of this diagram does not have a question mark. So this is just determined by general relativity. You can calculate this very accurately, how two black holes come together and merge. But unfortunately, all of these previous processes has a lot of dirty astrophysics, which is not very well understood. So there are lots of parameters that you can fine tune in these models to try to match the observed distribution. But what about spins? So you can measure spins of black holes using electromagnetic observations, and you can compare this to the gravitational wave observations. And also you can infer from theory what the spins of black holes should be from the isolated binary evolution. But just based on observations, you can see that. So if you have a star dumping mass onto a black hole, there's an accretion disk around the black hole, and the accretion disk at the center of the accretion disk, the size of the accretion disk depends on the spin of the black hole. And if the spin is higher, then the spectrum, then the gas can approach the black hole to a smaller separation, which means that the temperature of the disk will be higher and the spectrum shifts to higher frequencies that you can use to measure the spin of the black hole. So if you do this, you find that systems in which you have a black hole and a massive star, which will ultimately produce a black hole, those systems, so these are so-called high mass X-ray binaries. There are 3 of them. All of them have high spin. So the Kerr parameter is higher than 0.8. And the spin is expected to be aligned with the orbit because of tidal interactions. So this is already in tension with LIGO data, which seems to show just 0 spin, so distribution around 0. So here I'm showing the LIGO detections on the left-hand side, and on the right-hand side, I'm showing some models which use different prior distributions for the intrinsic spin magnitude of the population of sources and the relative orientation of the spins in the model. So if the spins are drawn from an isotropic distribution, then no matter what the prior distribution for the spins is, you get a peak around 0. So if you draw spins from an isotropic distribution, then this component around the total angular momentum will naturally by symmetry be peaked around 0. But if you have high spins and they are aligned with the orbital angular momentum as expected from tidal evolution, then you get this curve, which obviously has a high effective parameter. So this is, you can compare the two and basically rule out this possibility. The other option is n-body simulation, so dynamical encounters. And here I'm showing you the simulation of n particles moving in a globular cluster. So they are attracting each other gravitationally, and they are moving around. And ultimately they form binaries in the inner region, and the binaries eject stars out. So in the simulation, the simulations show that these structures are transient. They eventually disperse and vanish in the universe. So the only reason we see globular clusters at the moment is because there wasn't enough time yet for them to disperse. But during this time, they can produce mergers in large numbers. So there are different dynamical processes which take place. So you have a dense population, and you can have 3 objects come close. One object can be ejected and during this dynamical encounter, and the remaining 2 stars will not have enough energy to go back to infinity, so they naturally form a binary. So this is how binaries can form in globular clusters. And once you have a binary, another object can come by and interact strongly with this binary, and usually what happens is that if a more massive star comes in, then it can replace one of the components of the binary. And so you can form a black hole binary easily from a stellar binary just by interactions with single black holes. And once you have a black hole binary, interactions with further interactions with stars will remove energy from the binary and cause the binary to shrink and merge. Also, the black holes are more massive than the stars, so they will naturally sink to the center of the system by dynamical friction. And then you will have so much higher density in that region and higher probability for all these events to take place. So the general expectation of these dynamical effects is that the mergers will be more likely for the heavier objects in the population. And you can look at the distribution of mergers in simulations. And this figure is taken from a paper in 2016, which we produced just before the first observations, but then we put here the first 2 detections of gravitational waves. So here we ran Monte Carlo and n-body simulations for different initial conditions. So the problem here is that you don't really know what is the mass function of black holes to begin with, but we just put in something, and we put in the black hole mass function taken from population synthesis codes of stellar evolution, Baczynski 2004, and also just phenomenological models with power law mass distributions with different exponents, mass to the -3, 2, or 1, for example. And we run the simulation and measure, for example, the probability of merger for different masses, total mass binaries. And what we found is that the merger probability is strongly skewed towards high masses. because, as I said previously, you expect higher mass objects to merge more easily. And this is, so independently of the initial conditions, we get that the merger probability scales with the 4th power of the mass in the simulations. And, but of course, the higher mass objects may be rarer in globular clusters. So you could still have mergers, you can still observe mergers with low mass objects in globular clusters. So that depends on the mass function, but not the probability of merger. The other thing that you can do is plot the mass, plot the rate of mergers in this 2-dimensional diagram of mass ratio and total binary mass. And you can see that the prediction is that the mergers will be dominated by close to equal mass mergers. The unequal mass mergers will be very subdominant. And what's interesting is that there's this population of mergers. Maybe 7% of the mergers could be mergers of black hole remnants, so merger remnants merging again. So you can have black hole mergers, if they happen inside the cluster, they can merge again with another black hole if the merger remnant is not kicked out from the cluster during the merger by gravitational wave kicks. So if you compare these two observations, they show evidence of hierarchical mergers. So indeed, some of the black hole binaries observed by LIGO and VIRGO have high mass, which I showed earlier. And these mergers are likely, many of these are likely 1G plus 2G, meaning that first generation black hole merges with a second generation, meaning a merger remnant of 2 first generation black holes. So there's evidence for 1G plus 2G mergers, could be 5% to 0.05% of the full population. And there's also evidence of 2G plus 2G mergers, which is a small fraction of this population. So you can use this to put constraints on your models. And what about spins for the dynamical channel? Well, you form binaries by chance during encounters. So you expect the spins to be isotropically distributed. And you observe, in that case, you expect them to peak around 0 for this component. And they do peak around 0 apparently. So I would say this is consistent. But there may be a problem with the rates. So just if you simulate the rate, the merger, so simulate the evolution of these globular clusters in isolation, then you find, so simulations show that the merger rate is 6 per gigaparsec cube per year, where the observed rate, on the other hand, was between 15 and 39 per gigaparsec cube per year. And you can understand, so this number is 6, seems to be an arbitrary number, but you can understand it from first principles. It doesn't depend sensitively on the initial conditions, for example, because you can follow the following argument. So let's suppose that you have a number of black holes in your globular cluster, and each of them merges once in a Hubble time. So this is maybe an upper limit for the merger rate. You know how many stars you have in a globular cluster, so you can just calculate how many black holes you expect to have if black holes form from some above some critical mass, and you expect 0.3% of the stars to turn into black holes. And so if all of them merge once, then you know how many globular clusters you have in the universe. So what is the density of globular clusters? And so you immediately have a prediction for the rate of mergers. And this is the upper limit. If each of them merges once, you get 40 per gigaparsec cube per year for globular clusters. And if you do the same thing for galactic nuclei, you get a similar number. But the simulations show that not all of the black holes merge in the simulation, but only 20% of them form binaries and only half of them merge. So you lose a factor of 10, roughly. But of course, this is a very simplified argument, but still you come up with a number which is close to the predicted number from simulations. It's around 6 or 4 per gigaparsec cube per year. So this is surely cannot explain all the mergers that we see. So this is coming back to this point. So So this is some of the problems of these models. So another idea could be that maybe you need all of these different channels at the same time. All of them contribute equally to the observed merger rate, and maybe that's how you can explain the mergers. But what I will try to show you here is you can come up with new ideas, and that may be useful to start from scratch or tune the previous models to explain the mergers. So this is 3 different ideas. I will just mention them briefly and discuss mergers in AGN then in a little bit more detail. So first idea is disrupted globular clusters can contribute to the mergers. So it turns out that, so as I told you, globular clusters are transient they are dispersing and evaporating all the time. And so naturally, in the past, there were many more globular clusters than today. And the previous episode, the previously disrupted globular clusters could contribute to the mergers that we see today. So this is idea number 1. Second idea is that black holes are not isotropically distributed in the universe. And if they form disks, for example, during globular cluster mergers, then maybe the rates will be different. Third idea is that mergers can take place in gas environments, and gas can help to bring the black holes close. And for example, in active galactic nuclei, where you have a supermassive black hole and a gas disk around the supermassive black hole to produce AGN activity, that can help to bring in the binaries and merge them. So let me go one by one. So disruptive globular clusters. So here, this is a very well explored idea in the past. So there's a paper by Gnedin, Ostreicher, and Tremaine, for example, in 2014, which has shown that to explain the present day distribution of globular clusters in the Milky Way, you need to start from a much larger population of 8,000 globular clusters shown here. And then if you do that, then you will arrive at the correct radial distribution and also the mass distribution that is observed in globular clusters. So you have to start from 8,000 globular clusters, and they can produce mergers, black hole mergers that may, the mergers have some delay. You need some time for the black holes to come in and form binaries and then to ultimately to merge. And that can happen much later than how the globular cluster is being disrupted. So here I'm showing the result of these calculations with Giacomo Fragione, in which we took this into account. So we took into account the contribution of previous merger episodes, or previously disrupted globular clusters, and this increased the rates. But the rates were increased only by a factor of 3. So going from 6 to, let's say, 18 for the most typical model, but there are error bars. So maybe it's because of the error bars that there are so many mergers in the actual universe. So we don't know actually the true number of globular clusters in the universe. This has some error bar, and maybe it's higher than nominally thought. And the other thing that you can do is to plot the redshift distribution. So at earlier times, obviously the rates must have been higher because there were many more globular clusters, and you can test this with future observations with LIGO. And there are more recent papers. Rodriguez and Luke, for example, did a more accurate model for globular cluster formation and evolution and found this type of redshift distribution. So you can just look for this type of redshift distribution in LIGO data, and then this can be used to test the models. The other thing that you can do is to predict the mass distribution of the mergers. And this has been done recently, and you can compare to the LIGO data shown here with green line. There doesn't seem to be a good match, but okay, maybe this is not the only model which contributes to the mergers. The other idea is that black hole disks contribute to the mergers seen by LIGO and VIRGO. So this is a bit surprising from the point of view of classical astronomy. So what you see in the sky is that these globular clusters are isotropic, more or less. They are spherically distributed. These are spherical islands of stars with radius of 1 to 10 parsecs. But you only see the stars. You only see the basically the old stars in these populations. There are no young stars. And so naturally, you don't see the black holes. It turns out that there's a dynamical process which brings in the objects, which brings in the more massive objects into a disk configuration from an anisotropic configuration. So if you start the globular cluster from an initially anisotropic distribution, suppose even if you have spherical systems merging together from different directions, you will get an initially anisotropic distribution. And what happens is that due to this process called resonance relaxation, the more massive components in the system will tend to segregate into a disk structure, and the low mass components will become isotropic. And so this is shown by this the result of this Monte Carlo simulation, which shows the inclination distribution of angular momentum vectors. So it's basically the z component of the angular momentum vector divided by the angular momentum vector magnitude on the vertical axis, and the mass on the horizontal axis. So you can see that for low masses, the distribution is basically isotropic. It doesn't depend on, so everything has the equal probability. But if you go to high masses, then the objects cluster in one direction. So the angular momentum vectors cluster in one direction. So if this is true, then this would change the paradigm of globular cluster dynamics, because all of the previous models assumed the globular clusters were isotropic, and they found, for example, the process of core collapse, which central regions condense, the outer regions expand, and central regions form binaries, and the binaries cannot ultimately merge, but all of this assumed an isotropic distribution. Now you have to start over and do everything for this type of anisotropic distribution, particularly for the black holes. And so this is work in progress. I cannot show you results here yet, but just to flash this idea that maybe this will help to explain what LIGO sees. What I would like to discuss is mergers in active galactic nuclei. So you have, so around the supermassive black hole, you often see a gas disk. And the question is what happens with the stellar mass black holes embedded in this gas disk. And so the idea is that if you have a nuclear star cluster surrounding the supermassive black hole, they will, some of them will cross the accretion disk. And during these disk crossings, by dynamical friction, they will get captured in the accretion disk, depending on the initial inclination. This happens relatively fast, within 10 megayears, and then you merge the black holes. The gas brings in the black holes and merges them, and brings into sufficiently small separations such that gravitational waves can merge them. And this happens in less than 1 megayear. So this process is relatively fast. And so then you produce a merger, and it's really interesting that the merger happens in a gas environment. So it may not be completely dark in electromagnetic bands, but you have a chance for electromagnetic emission. And in fact, there was an AGN flare observed close to a LIGO event from a similar direction. So that's exciting. Maybe this process happens, but who knows? The luminosity of the electromagnetic emission is not clear if it should be observable, because it's a stellar mass. If it's a stellar mass system, you need extremely super Eddington luminosity for it to be observable at such distances that LIGO sees sources at. So the other thing that you can do is to do simulations. So we have a series of papers with Hiromichi Tagawa and Zoltán Hajman, where we simulate in a semi-analytical framework what happens to black holes in these environments. So we take into account the fact that the objects can get captured in the disk by dynamical friction. So we put in basically these prescriptions for the different processes individually, and then we evolve the system using these prescriptions. For example, we take into account disk capture, also dynamical binary. So we take into account dynamical binary formation during three-body encounters. But what's interesting here is that even during single encounters of single objects, you can form a binary because the gas can remove the excess kinetic energy of the system. So this cannot happen without dissipation. So in a globular cluster, you will never form a binary during single encounters, only if they come very close such that gravitational waves form binaries, but that's rare. Here you can form them much more easily. So you form binaries easily, and then you can bring the binary separation to smaller values after binary single interactions and also interactions with the gas disk. The binary forms a circumbinary disk, which can help reduce the separation, and then ultimately gravitational waves can merge the binary. So here's a simulation. This is with Connor Rowan, graduate student, of two objects orbiting in the accretion disk around a supermassive black hole. So we're just simulating, so this is an SPH simulation of an accretion, of an annulus of an accretion disk. And you can see that there are two objects. They form these density wakes within the disk. So the objects are already completely embedded in the accretion disk, and they interact with the disk, and they form these density waves. And so now we're just zooming in to see what happens, and we notice that the color scheme now changed just because we made it different. And ultimately, in the simulation, the binaries come together, and the gas helps to form to make the binary permanently stable, a binary, and to reduce the binary separation. So in the simulation, the binary forms a mini disk, and the gas can drive the binary to smaller and smaller separations, such that the gravitational waves can ultimately merge the binary. So this is very promising. It really happens. If we tried also, if we remove the gas in the simulation, then obviously you don't form a permanent binary. They can come together and they can have multiple encounters, but ultimately they will be ejected, not in gas. And so here's the result of the semi-analytical simulations. So here I'm showing you what happens with one of the binaries in the simulation. In the top panel, I'm showing the separation and the radial position in the AGN disk. So you can see that the separation changes, and also the center of mass of the binary also moves, because the binary migrates similarly to how planets migrate in protoplanetary disks. And the separation decreases, and here I'm showing the velocity of the binary with respect to the gas. So there are episodes in which the binary is embedded in gas and has a small relative velocity for the center of mass. But sometimes there are binary single interactions, so they can interact with third objects flying by, and those can remove the binary from the disk, but then the binary gets captured back into the disk. And so there are these different episodes of binary single interaction and gas episodes. And we can track what happens with the spins in this simulation. The binary single interactions will randomize the angular momentum vector of the binary. So the orbit of the binary can be altered, but it will not change the spin of the individual black holes. So the spins will be expected to be aligned in these configurations with each other, but not with the orbital angular momentum vector, typically. So this is a very specific prediction that the chi-effective parameter will be clustered around 0, because relative to the orbital angular momentum, there's no preferred direction. But there's still, the two spins are aligned with each other. So this is a prediction that can be tested in principle in the future. And so we can follow the distribution in time And so I'm showing what happens in different snapshots at 0 mega years. This is the initial conditions. You have some pre-existing binaries at these separations. These separations shown on the vertical axis and these distances on the horizontal axis. And but you don't need these pre-existing binaries because you form binaries by this gas capture mechanism shown here with cyan colors. And the binaries evolve, and ultimately they merge at here in the simulation at 0.01 parsecs. So the separation can be reduced greatly. And some of these binaries will, so this is how they evolve in terms of gravitational wave frequency as a function of location in the galactic center. And so you can see that many of these binaries will be, well, initially they are driven by gas effects, and then they are driven also by dynamical friction, but ultimately they are driven by binary singleton scattering. So this is important when the separation is smaller. This turns out to be in the LISA frequency band. So these objects will be emitting already in the LISA gravitational wave band, while they are still experiencing binary single interactions. And ultimately, gravitational waves will reduce the separation and increase the frequency from the LISA band up to the LIGO band. And it turns out that this type of source population can explain some of the outliers in the distribution of gravitational wave events that have been observed by LIGO and VIRGO. So here I'm showing some of these interesting objects. So here's an object for a merger in this so-called mass gap region. And so this is just in the region, which is in the region consistent with the simulation. So after the simulation, we can generate these probability distribution functions for the different parameters of the mergers. And this is shown by these shaded regions, and which extend to these sites where LIGO events are observed. And also we can plot the spin of the black holes merging. And there's one event which was detected to have a non-zero spin with large error bars. And also there's the chi-effective parameter, also the perpendicular parameter for the spin component, shown to be non-zero for one of the sources. And this is very much consistent with the prediction of this channel. We can also make estimates for the rates, but of course, this ends up being very uncertain. But we understand the sources of uncertainty in these models. But in any case, the rate of mergers ends up being between 0.02 per gigaparsec cube per year up to 60 per gigaparsec cube per year. So here for the higher values, you can see that it's even higher than the observed rate. So this is not a limitation for this type of model. So in principle, all of the mergers that have been detected could be coming from this one population. You can look at the actual distribution of spins if it's consistent in terms of chi-effective. The error bars are still too large to decide, but in the future this may be possible. And the other thing that you can look for is the eccentricity of these mergers. It turns out that it's very interesting that some of these, so here's the predicted eccentricity distribution on the right-hand side. It turns out that there's the eccentricity is typically around 10 to the minus 2 when in the LIGO band at 10 Hertz, which may not be distinguished from circular sources with LIGO, but some of the sources have high eccentricity, and this is because during three-body encounters, you have a chance for merger, and you don't have enough time for gravitational waves to circularize the merging binary because it forms with a very small periapsis distance. And so some of these mergers will be highly eccentric. And in fact, there was one source which has been claimed to be possibly highly eccentric. So this is very exciting. And in the future, once we will have a large number of detections, eccentricity may be one of the ways to discriminate sources and maybe rule out this population. I think I'm out of time, so but I've already reached basically the end of the talk. So you can make predictions for different model parameters. Then you get different distributions for the eccentricity. But in general, I think this is very exciting. So AGNs can maybe explain the mergers that LIGO sees, and there are some distinguishing features that can be used to specifically confirm or rule out this type of source population. And in summary, I hope I have convinced you that this is a very interesting field to work on. So there are a large number of detections, and the number of detections will be just increasing with time as the instruments improve in sensitivity. And gravitational waves offer a new type of probe of astrophysical systems. You can test globular clusters. You will be able to test, for example, if black holes form disks in globular clusters, or if they are spherically distributed. You will test interactions with gas disks, such as AGN. And this is important because it turns out that if you put in stellar mass black holes in AGN, you can calculate what is the back reaction, what is the heat generated by accreting stellar mass black holes in AGN that can influence the AGN itself. And it turns out that the heat generated by the stellar mass black holes embedded in AGN is larger than the viscous heat generated by just the normal accretion activity of AGN. So maybe stellar mass black holes are fundamental in even understanding AGN themselves, regardless of gravitational waves. And of course, in the future, you will have even more gravitational wave observations. There are new instruments. Kagra has joined the collaboration, which is really exciting. There's a new instrument being built, LIGO India, to expand the network, to improve the detection capabilities and localization capabilities of the network. And there are plans for upgrades, LIGO Plus, Cosmic Explorer, Einstein Telescope are all being planned to increase the range of detections to slightly lower frequencies, and just the sensitivity will be increased greatly. And in the future, LISA will, of course, be extremely exciting because you can probe events at completely different frequencies. So let me stop here, and sorry for running a bit late on time. Thank you very much.
Bence. Thank you very much. So are there any questions for Bence? Not sure. Okay, Gary, please.
That was a wonderful talk, Bence. I learned a lot. I took 7 pages of notes.
Thank you.
So with my student who's here, I think Eduardo Vitral, we've been doing dynamical modeling of globular clusters, looking for intermediate mass black holes. And we also thought about stellar mass black holes because we found excesses of stars beyond the normal stars. So there could be stellar mass black holes. And so I was wondering whether the rate of black hole mergers could be more important in globular clusters if you assume a top-heavy initial mass function. After all, globular clusters tend to be very old objects. They might have formed at times when the IMF was different.
That's
thought about that.
That's a good point. That's a very good point. So in fact, yeah, this is one of the interesting uncertainties. That's why the error bars are so large in all of these diagrams. One of the reasons why the error bars are so large here. Yes, if you have a very top-heavy IMF, then you will naturally form heavier stellar mass compact objects, and that can influence the predictions. So you will form many massive black hole binaries and merge them. But ultimately, I think it's hard to exceed this upper limit that I was trying to show somewhere in one of these slides. Yeah, here. Because even if you make well, yeah, if the mass function is very top heavy, then you will have just more mass in black holes. So maybe you will increase the upper limit as well. I agree. So yeah, that's a good point. And I should note that in galactic nuclei, the metallicity is observed to be high, meaning that you will not even form these high mass black holes, which are observed by LIGO and VIRGO. So you may need low metallicity environments such as globular clusters to explain the high mass sources. But on the other hand, in galactic nuclei, the black holes experience so many mergers, and they interact with the gas so much that they can grow. So even if you start from 15 solar mass black holes, for example, you can easily grow to the values which is observed. So yeah, but in all cases, the mass function is an important unknown, which influences the result a lot. But hopefully, once we will have thousands of LIGO VIRGO observations, you can really dig deep into the mass distribution and maybe use the models to learn something about the mass distribution of black holes in these systems.
Okay, thank you.
But, yeah, good point.
Any other questions? Maybe I can, Hélène, please.
Yeah, thank you very much for this very interesting talk. I'm wondering what you think about programs, observational programs, which try to detect electromagnetic counterparts, because the idea was mostly in the past that binary black hole merger should not emit a lot of electromagnetic radiation, but with this new idea on the pathway to mergers, it seems that there might be a rather strong electromagnetic signal. So do you think the probability to detect something could be important, or are fluxes very faint, very weak, and may be very difficult to detect?
Yeah, thank you for this interesting question. Yeah, that's I think that's generally very exciting. It's a very high risk, but also high gain endeavor. So I think it's not obvious if electromagnetic counterparts would be detected, even if the mergers take place in accretion disks, just because it depends on what type of emission is being produced during the merger. But it is, I would say, it is not guaranteed at all that this will be observable. So if the emission is Eddington limited, then there's no hope of detecting anything. But perhaps it's not Eddington limited. It's a violently non-stationary process. So it's not clear. But what I should say is, for example, if you do order of magnitude estimates for how much energy there may be to radiate, if, for example, objects are crossing the accretion disk, there can be shocks, and that can produce electromagnetic emission. And that has been used to estimate the luminosity of some of these sources. But that, I think, implies relatively still too low luminosity, unfortunately. But so there was this one paper by Graham and company, which is highlighted here, which argued also with a very simple estimate that maybe one of these sources could produce, at least energetically, has enough energy to explain some of these flares that have been observed. But I think this is very, very difficult to make. Well, it's an interesting question to think about and make predictions for. But another question is, if objects are crossing the accretion disk, for example, do they produce electromagnetic flares? would the flares of merging objects be stronger than the flares produced by disk crossing objects, for example? So it is not clear that the mergers themselves will produce the most luminous emission. Maybe it will be just the process of capturing objects in the accretion disk. So there are lots of possibilities, but I think it's worthwhile. So even if, for example, even if we don't identify an individual electromagnetic counterpart to a particular merger, you can do it maybe statistically. So ask, is the electromagnetic transient in terms of a full population consistent with the gravitational wave distributions that you see? For example, you can measure the distribution of black hole mergers in the sky and calculate, for example, the 2-point correlation function between black hole mergers. And you can compare that with the 2-point correlation function of AGN, for example, which is not the same as the 2-point correlation function of galaxies. So statistically, there's a chance to detect or confirm these AGN models, even if using electromagnetic observations, because in that case, you're using the 2-point correlation functions of AGN without actually identifying the counterparts. But yeah, unfortunately, I cannot give you a full answer, but I think it's worthwhile to look for these sources, much more than without, sources in the absence of gas will be much more difficult to see, and maybe probably impossible.
Okay, Thibaut?
Yes, Thibaut Damour, very nice talk. I wanted to ask a question about the large masses observed for some black hole mergers. At the time of the first LIGO observations, it was emphasized that the group of Belczynski, Bulik in Poland had predicted that low metallicity environments would contribute to, what is the status of this idea? It's no longer considered as a good explanation of the large masses?
I think, thank you for the question. So yeah, I just removed this, removed this slide from the talk just before the talk because of time. But it is true that Chris Belczynski's group made predictions for the masses of the most massive black holes to be observed with LIGO even before the detections. And their predictions have changed in time. So originally, they predicted in 2014 that the masses could be up to 100 solar masses. 2009 and 2014-15, the maximum mass was up to 100 solar masses. So the idea was that the maximum mass is limited by this pair instability supernova. But, and of course, it also is very sensitive to the metallicity of the progenitor star, because if the metallicity is high, then the opacity is just so large that there's a lot of mass loss due to winds. But if metallicity is low and opacity is low, then you can form more massive objects up to this mass limit. But then in 2016, they realized that there's this pair instability pulsation mechanism, which has been overlooked in earlier. So here, there are pulsations of the progenitor star, and these pulsations can produce pair instability for stars lower mass than previously believed was necessary for pair instability to take place. So due to these pulsations, the mass limit decreased from 100 to 50 in the models, just explaining the observations. The first observation had 30 solar masses, so they were consistent with both the original model and this model. And But more recently, there are observations of black hole masses larger than 50 solar masses. So those may represent a problem. But most recently, in 2020, Chris Baczynski had a new paper which took the black hole masses back up to 100 solar masses. So unfortunately, these models have
uncertainties,
very big uncertainties. So it's difficult to make firm conclusions. But I think the spin distribution is important, may be important to test these models, for example, regardless of mass, or in addition to mass.
Thank you.
Any more questions for Bence?
Okay, maybe I can turn off recording, and we can just then continue discussions with Bence kind of